Good morning, class. Today we're going to be exploring methods in object-oriented programming. Now, methods, as you've read in the textbook, are really a form of message passing. They're a way of telling the object that you want it to do something, most often mutate its state, but there are some other potential uses for methods as well. And this is the big idea that was a shift from the earlier forms of encapsulation, where we encapsulated data together in a compound data type or a structure, and we had encapsulated library modules that would do the different functions, the behavior. Object orientation said, actually, let's take those and put those together. So that's really the big idea for today. So let's jump to our code. We're going to continue from this vector library project that we've been working on. And at this point, we've already converted our vector3 from a structure into a class. And we've declared a bunch of properties to replace the fields. Now, properties themselves are methods, like we talked about. These are specific accessor methods. But they're not the only kind of method that we would normally use with a class. So today we're going to explore those other methods, and specifically we're going to take the ideas that are in our actual vector math static class and move those into our vector3 class. That's really the core idea we're after now, is we're going to encapsulate both the state and the behavior within this vector3 object. So let's jump back to our vector3 object. I'm going to do something you may or may not have seen before. I'm going to declare a region for our properties. And at the end of our properties, we'll do an end region. And these are really just organizational tools in Visual Studio. Notice they use the pound sign in front of them, which indicates a preprocessor directive, but in this case it doesn't actually do anything with the preprocessor. They're just using that as a way of commenting. The benefit is then, once we've done that, we can click that little minus sign next to it and collapse that entire region of code. So now we have a region which is dedicated to our properties, and I'm going to declare a second region for our methods. And this one I won't collapse, because this is where we're going to write our methods. And as we talked about just a moment ago, we come back to our vector math library. We have the add, the subtract, magnitude, and then you've written the other ones for dot product and cross product and normalize and all of those operations. With object orientation, rather than having these in their own library, we would pull them into the class that actually they work with. So for example, here in our vector3, we would want a method for the add operation. And this is going to be a little bit different than the one in our library, because we're going to actually mutate, which means change, the existing state of the individual vector3 object. So instead of doing what we did in our library, which was take two vectors, add them together, create a new vector, and return that vector, here we're going to add a vector to this vector, the one that is represented by the individual object that has been constructed here. And when we do that, we are changing the state of this vector. That's one of the big ideas of object orientation, is that state and behavior encapsulated in an object, and that object mutates, it changes state over time. This is very different than a lot of functional programming languages, where a core idea is once a data type is created or a particular structure or object in memory, we don't actually change it. If we want a different version of it, we would create a new version, a new instance that has the changes. So our old one would stay the same. We call that an immutable data type strategy when we do that. And there are very valid reasons for doing that, especially in concurrent programming. But in object orientation, that's not the typical pattern. The typical pattern in object-oriented programming is to have an object that will mutate and change over the the course of the program running, executing, to reflect some real-world object that is also potentially changing and updating. So in this case, we take our vector3 and we're going to name it actually other. Let's see that I didn't quite do that right. And to this vector3, we are going to add to our own x, y, and z components, or those properties, others x, y, and z. Now the this dot is optional, it is understood, and that's why this kind of grays out, that this dot x and x refer to the same field, the same property in this case. Or we could also, if we used a private backing field, we could set the private backing field directly. That's perfectly fine as well. But the core idea is that we're going to set the x, y, and z to be this x, y, and z plus the other x, y, and z. So like this dot x, the existing value, plus the other value. Now you probably have seen the syntax where we say plus equals. This just means exactly the same thing as this line. It's just syntactic sugar for saying take the current value and add to it another value. So these are equivalent. You can do it either way. So that is our add. And our subtract would look very much the same. Except we would subtract the two vectors. So x minus equals other dot x, y minus equals other dot y, and z minus equals other dot z. So once we've done that, we have now those two methods. How would we use those in practice? Well, let's jump back to our program, our console program. And here let's do, take our 1 vector. And now we can call subtract on it. We'll subtract 2. And then let's write that out. So console, in fact, I'm just going to copy the line where we did it up here because it's exactly the same code. So we should see printed that we had the values of 1, which we set to 1, 1, 1. And then when we get down to this 1 dot subtract 2, we're subtracting vector 2 from vector 1, so minus 2, minus 2, minus 2, which should leave us with vector 1 now holding the values negative 1, negative 1, negative 1 for its x, y, and z. Let's go ahead and run that program to see if that's the output that we see. And there you can see initially vector 1 has 1, 1, and 1. And after we perform that subtraction operation, it now has negative 1, negative 1, negative 1. So we've actually mutated the state of the vector we have stored in the variable 1. So that 1 is a reference to that specific object that was created that had a value of 1, 1, 1. And then we took that object and we asked it to subtract the value of 2, 2, 2 from all of its components. And that's where we get our result. Now we also would want to write tests to test this. So if we jump into our test project, vector math unit tests, we are going to add a new test to actually do this operation. Now we could adapt the existing test, but I want to leave them for a very specific reason we're going to come back to in a moment. But we would go ahead and, in this case, we can use the same incoming data because that's not going to, oops, except I don't want that one. I want the subtract and the sum. So the sum and the difference. So add returns vector sum, and here, let's call this add method, add class method, we'll call it that. Instance. Actually, it's an instance method. We'll call it an instance method because it's a method that affects a specific instance of the class. So we'll call it add instance method. And here, when we do the add operation, instead of doing it this way, we are going to use that new method we wrote. So we'll call a.add, and we'll add to it b. And then we're going to assert that instead of using c here, c.a and c.b and instead of using the vector c, which no longer exists in this scope, we're going to use that vector a, which should be mutated. And it should have the values that we're passing in as our inline data here, which is the x, y, and z of the result of doing that sum. We'll do the same thing with our subtract. And we'll explore writing tests in more detail, but this is a good kind of first getting used to it. Subtract instance method. returns vector difference. And again, we're going to take our A, and in this case, we're going to call subtract. It only takes one variable, which is B. And then because we're mutating vector A, we're going to check that vector A's values after the operation are what we expect them to be. So now if we run these new tests that we just wrote, and you can see the new tests are in blue. It's telling us that they're new. They've just been added. We run it. They pass. We've done our work successfully. That helps us know that our add method, which is an instance method on the class, works with the same data that we supplied to the original static method that was part of our library. So we know that those pieces are working well. Let's go ahead and implement one more method on our vector class. And the one that we're going to do next is the magnitude. Now, if we think about it, what is the magnitude? Well, it returns, and we can go back to our vector math library. It returns basically the length of the vector. We take all of the components, we square them, and then we take the square root of that, and we return that value. Now, we're not going to mutate the state of a vector into a double that is the length of the vector. In fact, if we think about it, the length of the vector, the magnitude of the vector, is really a property of the vector. It is something that is specific to the current state of the vector, and in that sense, it actually makes more sense to use a property than a method, though we could have a method which returns it. So let's go ahead and implement that one as a property. So we go back to our vector 3, we're going to expand our properties, and we're going to declare a new property for magnitude. And that magnitude vector is only going to have a getter, so no setter, because it's derived from the x, y, and z components. We can't set the magnitude of the vector. If we did, we'd have to do some really, think about what that really means. That would basically mean we want to change the length of the vector, probably want it to face in the same direction. It is possible to do that mathematically, but that's probably not what most people are thinking when they ask for the magnitude. They're not thinking, I'm going to change the length of the vector. They're thinking, I need to know what length this vector actually has. So it makes sense to use a get-only property. And because this property is derived, we're going to actually look at the other aspects of the state. So in this case, return the square root, math.square root of our x property plus our y property squared plus our z property squared. And again, in this case, I'm squaring them just by multiplying them by themselves. We could also use math.pow with a second argument of 2, take it to the second power. They're equivalent meaning, so either one will work perfectly fine. And now we have magnitude, and that is defined in this case as a property rather than a method. We could have also written it as a method and had a return type of double and done the calculation and returned it. That's okay. The difference in the two is how they actually look when we use them, like for example in our console. So let's go back to that console program. So here we're going to call the magnitude. So if we had written that as a method when we called it, let's do the magnitude of 3. We'd call 3.magnitude and we have the open close parens. But since we declared it as a property, we don't call it with the parens. We just call the name, and that will give us the return value. So we use it as though it was a field, even though we know it's actually a method. All right, let's go ahead and run that and just see what our output is from the console app. You can see there that it told us our magnitude is 5.196, which is exactly what the magnitude for vector 3 done with the static library was. So that piece works exactly like we'd expect. We jump back to our test. Let's go ahead and take and transform that test to do the calculation of magnitude. So here, instead of just magnitude returns vector, let's do magnitude property returns vector magnitude. And we don't need to do this calculation anymore because we can just call vector A dot magnitude. And that's going to calculate the magnitude and check that is actually what we expect. The other thing you might be wondering about, what is this 12 doing here in this equals? So this assert.equals basically checking, is this value the same as this value? So what's this third one? Well, that is the precision. That's telling us how many decimal points to look at. So if you think back to scientific notation that you probably learned in high school and significant digits, you said we only care about up to a certain number of digits. After that, we can kind of throw away the partial part. We do the same thing when we're asserting with doubles and floating point numbers, because floating points have a small amount of error that can creep in as you do operations on them because of the nature of a floating point representation. So we want to say how precise we want to be. We say within 12 decimal places is good enough to say that these are the same number, even if they're slightly different beyond that level of precision. In our other, when we're working with, for example, integers and things like that, like here, notice the assert.equal, we're not checking for that precision, and that's okay, because in this case, we're setting explicitly what those values should be. They should be equal. We haven't done any operations on them, so we don't need to worry about that floating point error creeping in. Also with integers, with strings, with anything like that, floating point error doesn't exist. It's specifically with floating point numbers. So those are the ones we need to worry about. That's also why we use decimals, which are a fixed point notation when we're working with money, because we don't want money, we don't want the incremental pennies, fractions of pennies to get lost in either as we do our calculations. We want them to actually be fully accounted for. So that's a standard thing we do in C#. All right, so that shows us how we can write those methods. Now I want to talk about another form of method, and this is why we haven't gotten rid of this stuff yet, is we can actually take these static methods and we can move those into our vector3 as well. So let's go ahead and take all three of these, and you will take all the ones you have. I'm just going to cut them, and I'm going to drop them into the vector3 class. I'm going to create another region for them. I'm leaving these as static methods. So these become, when we declare a static method within a class, this is what we sometimes will call a class method, because it's run at the class level. So if we go back to our tests, well, actually let's go ahead, at this point we can just delete this vector math library. We don't need it anymore. And we're going to go back to our vector unit math tests. And you'll notice that as soon as we deleted that class, we're going to start getting some things underlined in red. It's saying vector math doesn't exist anymore. Well, we moved that add method to vector3. So we can call vector3.add, and suddenly it's happy again, because now we're using the static method that's declared in the actual class. So this also allows us to do module type methods within the class that actually they represent. So we're just going to go through and tweak all these, oops, so that they are using vector3 instead of vector math. So we do have one little issue that comes in here, because the magnitude actually already exists as a property. Now we can have two methods named the same thing, like here we have add, and here we have add. And notice that those are perfectly happy. There's no complaints about that. And this is one of the other core ideas of object orientation, the idea of dynamic dispatch, which goes along with message passing. It basically says we can have multiple methods named the same thing as long as the language has a way of sorting out which one we're actually referring to. And when we call this add, we're calling that on an instance, an actual object. So a variable holding a vector3 object. When we call this one, we're actually calling it directly on the vector3 class itself. So vector3.add versus, in this case, 1, 2, 3, or A, B, C, or whatever we named our vector. So that's the difference. Now this one gets a little bit tricky because it's looking at a property, and that property has the same name, and it conflicts a little bit differently because technically the property named magnitude is taking in a vector 3 as well if it had a setter. Now it doesn't have a setter, but it's still tripping up the compiler. So what we can do here is, rather than calling this magnitude, let's just call this length, because they are synonyms. So we'll say that we have a vector length property, which will give us the magnitude, and that's going to be our static class name there. I think the rest of those should work fine because you're actually using methods rather than using a property. And that's one of the things you will want to do at this point, is go back, and now that you have the add and subtract method, you're going to want to implement the dot product as a method. Now, actually, let's go ahead and do that. I'll walk you through it. And why do we want this one to be a method where we wanted magnitude to be a property? Honestly, sometimes they're a little arbitrary as to which one you're going with, but it makes sense for the magnitude to be a property because that is something that's intrinsic to a vector. A vector has a magnitude. On the other hand, the dot product is an operation you're doing with a vector, so it makes more sense for that to be a method. And it's actually, dot product's probably not a good example because it takes another vector as part of its operation. Let's do normalize. So what does normalize mean? Well, normalize means we're going to take that vector and we're going to transform it so it's length 1, or it's a unit vector in the same direction as the original vector. So this is, again, a mutation. We're changing how the vector behaves. So in this case, we want to set our x, y, and z to be the length that originally was divided by the magnitude that it currently, the vector has. And that shortens all of those to the point that when you take the magnitude, they're going to be length 1. Let's go ahead and do that. Let's say x, and we can do divide equals by the magnitude. And because we declared magnitude as a property, we can just call magnitude. We can also say this.magnitude. We'll do the same thing with the y and z. So we're basically saying take the x, take the y, take the z, divide those by the magnitude. And we're also changing the existing x, y, and z. So after we do this, our vector should be unit length. And we can check that. Let's go ahead and just write a new test to cover that. And we're going to do a slightly different test. And we will actually have a chapter or a section a little bit later where we talk about tests and what those tests do. But I'll go ahead and show you that right now. So we'll have a public void, and tests never have a return type, at least in X unit, which is what we're using. And we give it a name, normalize. Makes a vector unit length. And actually, rather than a fact, let's go ahead and do a theory. A theory takes in a couple different values, and those are arbitrary. You decide what they are. We're going to do an x, y, and a z for the 3 components of our vector. We will create a new vector when we get in here. It takes that x, that y, and that z. And we want to convert that to unit length with that v dot normalize. And it's a method, so we do call it with the parentheses. And after we do that, it should have length 1. So we can say assert. And the first argument to our assert, in this case assert.equals, is what our expected value is. We expect it to be unit length. So 1, 0, and then we want to check the expected value, which v dot magnitude, we expect the magnitude of our vector to now be 0. And let's go ahead and put in that 12 so that we have the, and this is actually assert dot equal, not equals. There we go. So that should basically take the incoming vector, which we're going to make this a theory. And when we have a theory, we provide inline data. The inline data, what's in parentheses, is basically the values you're supplying for the x, y, and z in this function call. You can think about each inline data as being, call that test method with these values. So let's go ahead and do a couple arbitrary ones. Let's start with a vector 1, 1, 1, 2, 2, 2, and try 4, 8, 2. And you can just do an arbitrary number of these, but what you really want to do is cover all the edge cases. And if we think about this, what is one of the edge cases that we probably need to cover? Well, what happens if we give the 0 vector? That would be an edge case. So let's go ahead and test this. Another one might be throwing in not a number or something like that, or infinity, which are going to cause some weird things when we start doing calculations. So if we run our test explorer now, we go and we can actually just run these two tests that we've added. And if we have build errors, we have to make sure we fix those first. Let's take a quick look at our error list. Oh, we missed the vector math here because we changed that library name. So vector 3 and vector 3. And we changed this from magnitude to length. And you can see we run that, our magnitudes stay the same, so changing that library didn't change anything in terms of functionality. And if we run our test explorer now, let's go ahead and just run all the tests so we can redo those. Oh, missed something. What did I miss? Oh, that needs to be linked there as well. I'll run that test explorer one more time. And notice that the normalize, we have 4 failures. So if we look at the results from this test, it's telling us what the expected value was. And this particular one, it's running against the zeros. And notice assert.equal, the actual value we got was not a number, because you do division by 0 and C# gives you not a number. Look at the next one. So here we expected 1, we got not 1, and here we got, whoops, where'd my test explorer go? Come back. So you can see we missed something in our calculation. Our magnitude is not being, our normalization is not occurring the way that we expect. So something in there is failing to give us what we want. And this magnitude is giving us our expected values. And this magnitude is giving our expected values. So our magnitude is working correctly. Our normalize, for some reason, is not. And let's go back and look at that vector 3 class. And this is one of the things that we have to be aware of. So this looks perfectly fine, right? This is what we expect. We take the value, we divide it by the magnitude. But there's actually a very subtle error here, because this is a method call. Remember, a property is a method call, or a field is a direct access. Either way, this would be a problem, because what happens is we change our x value on this line, which means our magnitude is no longer what it used to be. It's a new magnitude based on this x being a different size. So now our y is doing its calculation with the new magnitude, which gives it an incorrect value. And then z, when we calculate it, uses the new magnitude that has both the modified x and y. And this is where we have to be very careful when we mutate state, because what we're actually doing is we're mutating the state during this calculation so that we're using slightly different state at each step of the calculation. How do we solve that? Well, the easiest way is to cache that value of magnitude. So we can go ahead and create a double and just go ahead and store the current magnitude in there. Now this is an instance variable, so our naming convention is we use lowercase camel case for the name, and I'm just going to call it magnitude as well. But now this magnitude is a magnitude that was grabbed at this moment in time before we modified the x, y, or z. So once we've made that change, if we go back to our test explorer and run it again, we should see all that normalization passing, with the exception of that very first one, because this one, again, does that division by 0. That was the one that was crashing. So how can we fix that? Well, we can actually add an expected value to our facts. And go ahead and say what that should be. So for all of these, we'd expect it to be 1. Except for the 0, 1, we'd expect it to be double dot not a number. That is what is defined as our expected outcome. And then instead of looking for a hard-coded one here, we can say expected. We take that expected value, we compare it to the actual magnitude, and if we go back and rerun our test, skipped it for some reason. There we go. 29 passed, we've got them all working. So at this point, what I want you to do is go ahead and finish writing the instance methods for cross product, which should return a new vector because you're doing an operation on the vector, but it should only take the other vector. So the same pattern that we did with the add and subtract, only this time you're doing a return instead of mutating the state. The same with the dot product. Go ahead and calculate the dot product as an instance method, returning a double. And we did the normalization method, and we did the magnitude properties. So those are all covered, and we've got everything we want. So finish those, and then go ahead and write the tests that go with it, which are basically just adapting the existing test like I showed you. And then go ahead and create your release and turn that in. And that should wrap you up for this exercise.